Assalamualaikum and good day to all of you. So today I will continue our subtopic chapter 5 part B, transformer. Okay, so last week I hope you all already watched the video that I uploaded in YouLearn, which are basic principle of a transformer and type of losses in transformer. So today I will continue a few more subtopics for chapter 5. Okay, so first of all, we will discuss the ideal transformer. So actually in transformer we have two conditions, which is the ideal transformer and practical transformer. So what is ideal transformer? So several assumptions on ideal transformer. First one, we neglect the winding resistance of its core, and then neglect its core losses, and assume all flux is confined to its core. So assume for ideal transformer no flux leakage, and then it means that when you neglect all the losses, type of losses, it means the efficiency of ideal transformer is 100%. So and then the practical transformer, the three variables that we neglected in ideal transformer is flux, winding resistance, and core resistance. So this is the type of losses happen in transformer. So this one also covered in the video I already uploaded in YouLearn, which discuss the losses in transformer, flux leakage, core losses. So for core losses, it involves three types of losses: eddy current, hysteresis, and mechanical losses. And then winding resistance or winding losses. Okay, so this is actually the important formula you have to remember that involve transformer analysis. So Vs over Vp equal to Ns over Np equal to Ip over Is. So S is secondary and P is primary. So this is your primary side and this is your secondary side. And also this one is transformer rating. So S primary equal to V primary, I primary. So S is actually transformer rating. The unit is in voltage, ampere. And then for secondary, S secondary equal to V secondary times I secondary. And then the turn ratio is Np over Ns. So N is number of turn at primary, and then over number of turn in secondary. So this is the basic diagram for transformer, which explain the coordination of primary side and secondary side. So example 1, 100 kVA, 4000 volt over 200 volt with frequency 50 Hz, single phase transformer has 100 secondary turn. So determine the primary and secondary current. So first of all, you have to identify the information given. So 100 kVA is your S. Okay, and then you have to know how to read your transformer rating. So this is the front voltage is your V primary over V secondary. So you have to know the front is voltage at primary over 200 is voltage at secondary, and then this is your frequency, and then you have secondary turn, which is NS. Okay, so this information you have to know how to identify. So the first one, determine the primary and secondary current. So using the formula of transformer rating, V primary equal to, S primary equal to V primary, I primary. So this one given, and then your V primary is given. So this one I will write back the information. So Vp equal to 4000 volt, and then Vs equal to 200 volt, and then the frequency is 50 Hz. Okay, so you just substitute from this formula. So now you will find IP. So IP equal to S primary over V primary. So you will get 25 amp. Okay, so for ideal transformer, this statement is very important. For ideal transformer, SP equal to SS. So rating at primary equal to rating at secondary. So from that, you can find the formula. This one also from this formula. So S secondary equal to V secondary, I secondary. So therefore, I secondary equal to S secondary over V secondary. So that's why you will get this formula. Okay, and then next one, the question asks you to find the number of turn at primary. This one is from the formula. Yeah, okay. So Vs over Vp equal to Ns over N. Okay. So, or you can write it as Np over Ns equal to Vp over Vs. So to get the Np, P equal to Vp Ns over Vs. So you just rearrange back this equation, so you will get this formula. So just substitute. So Vp is 4000, okay, times number of turn at primary is, and primary is 100, okay, times 100 over your Vs is 200. Okay, and then to get the maximum value of flux, so this formula is from part A. So you just substitute the formula to get the maximum flux. So Np is 100, okay, and then E is actually a voltage, okay, energy generated. So this one is equal to Vp. Okay, so EP or Vp equal to 4.44 times number of turn. This one is from part calculation for part B, 2000, times frequency 50 Hz times maximum flux. So use your calculator. Maximum flux equal to 9.009 microweber. So these are the example of transformer analysis. Okay, hopefully you can understand the example. Okay, this one also a few example. Other example for transformer rating. Okay, transformer rating is usually described in rating volt and apparent power. So this one is the apparent power is your S. Okay. So example, a transformer rated 2400. So this one you know V primary, and then this one is 120 is V secondary. Okay, and then this 48 kilo VA is your S. So this one you use this formula to get the IP. Same with, so Vs is same because we assume that the transformer is in ideal condition. So V for ideal condition, so ideal transformer condition, so Vp equal to Vs. So this statement is very important to analyze the transformer. Okay, next, practical transformer model. Okay, so modeling, this is the practical transformer model. So this is the few type of winding resistance and winding reactance at primary, and this one is at secondary. Okay, so the objective for this subtopic is you have to find the value of each winding resistance at primary and secondary. Okay, so these are the definition of important parameter for practical transformer model. So this one you can read by yourself, and then you can identify what is your IM, R1, X1, RC. So this is at primary side, and this is the term at secondary side. Okay, and then equivalent circuit of transformer. So these are the formula, the proven step to get the formula for each parameter. So each parameter have its own formula. So these are the steps. Okay, so from the step, so these are the conclusion for equivalent circuit referred to primary side. So Z1 equal to R1 plus J X1. So Z1 is here, and then Z2, this one is actually you refer to primary side, so equal to R2 plus J X2, and then the formula for R2 is N1 over N2 square R2, and then for X2, N1 over N2 square X2. So normally all the information for N1, N2, X1, R1, R2, X2 is given, but you have to find your own Z2 using this formula. And then this is IC is core current, and IM magnetizing current. So IC, IM, and then to get the value of I2 referred to primary side equal to N2 over N1 I2, and then value of V2 referred to primary side is equal to N1 over N2 V2. So how about the equivalent circuit referred to secondary? So the proven method, if the question asks you about equivalent circuit referred to secondary, you can get your information from this textbook. So normally, all the question we use equivalent circuit referred to primary side. Okay, so for further simplification, we can replace R2 by inserting R2 referred to primary in the primary such that the power absorbed in R2 is equal to R2. Okay, so simplify the equation, you will get R equivalent equal to R1 plus R2. So V1 over V2 square. Okay, and then so these are the formula you have to remember for R equivalent, and then X equivalent. So X equivalent equal to X1 plus X2 V1 over V2 square. So if ZE is the equivalent impedance of the primary and secondary winding referred to primary circuit, so ZE equal to RE square plus SE square Z2. Okay, so these are the simplified equivalent circuit of transformer. Okay, so this RE and XE is you use from this formula, XE and RE. Okay, and then ZE, we use this formula to get the value. So these are the equivalent circuit of transformer which refer to primary side. And then RC and SM can be removed to the left with very little loss of accuracy. So these are the next step for equivalent circuit refer to primary side. Okay, and then for voltage regulation, so this one is the formula for voltage regulation. So this one you don't have to remember the formula. Okay, so this is the example for voltage regulation calculation. So 5 kV, 5 kilo VA is your S, and then Vp over Vs. The single phase has secondary terminal voltage. When loaded, determine the regulation of the transformer. For this one, you use this formula. Okay. So this one, terminal voltage already given when loaded. So this is terminal voltage. This one, terminal voltage, or okay, so from this example, these are the formula you have to use. So no load voltage minus full load voltage over no load voltage times 100%. Okay, so this is no load voltage at secondary, okay, minus full load. When loaded, it means full load. then over no load voltage. So this is your no load 400. Okay, times 100%, you will get 3.1%. Okay, so voltage regulation. So this one you can read by yourself, no need to remember the formula. Okay, so I will skip this example. So this is actually the step how you draw the equivalent circuit referred to primary side. So you can study the step. Okay, transformer losses. So there are two types of transformer losses. You have copper loss, which happen at your winding, and then core or iron loss due to hysteresis and eddy current. So this is the formula for copper loss. Okay, and then the formula for core loss. Okay, and then transformer efficiency. So these are the formula for transformer efficiency. Okay, so transformer efficiency. For practical transformer, efficiency is maximum when variable copper loss equal to constant core or iron loss. So assuming the full load copper loss is P copper, the corresponding equation become P core equal to N square P copper. So N is fraction of full load kVA at which the efficiency is at maximum. So at maximum efficiency, therefore the transformer output is, so kVA output or S. So kVA is your S actually. So S output equal to fraction of full load times, so S input. Okay, N times, so this one is S output. So example, so you have a 500 kilo VA transformer has a full load a loss of 4 kilowatt and core iron loss is 2.5 kilowatt. So the question asks you find the kVA output which the transformer efficiency is at maximum. So for A, at maximum efficiency, so P core equal to N square P copper. So P core is already given, or core iron loss is 2.5 kilo. So 2.5 equal to N square times 4. 4 is P copper. So 4. Okay, so this one is actually in kilo, but you can cancel out. So that's why this solution neglect the kilo unit. So you will get N equal to 0.789. So therefore, so output kVA at maximum efficiency, so equal to N times kVA input rating. Okay, you will get 395.5. Okay, so this formula is from, so S output equal to N S input. Okay, so N is from this calculation 0.791 times your S input is 500 kVA. So you will get this value of S output. And then the next question, efficiency, taking the load power factor is 0.75. Okay, total loss is equal to 2 times P core. So why 2? Because you have 2 core. Okay, so you will get the total loss is 5 kilowatt, and then output power is equal to, so S output, so times your power factor, so you get 296.625 kilowatt, and then input power is equal to output power plus total loss, so we get 301.625 kilowatt. And then maximum efficiency is equal to 1 minus losses over input power times 100%. So you will get 98.34. Okay, and then transformer efficiency. Okay, so for transformer efficiency, so this subtopic is very important for you to understand. Okay, so please make sure you understand the step of example for calculating the transformer efficiency. Okay, so you have efficiency at full load, which equal to full load S times power factor over full load S times power factor plus P short circuit plus P open circuit. So also for any load equal to N times full load, the efficiency is, so efficiency at N times full load is equal to N times full load S times power factor over N times full load times power factor plus P open circuit plus N square P short circuit. So this one, please understand the analysis. Okay, so we look into example 2. Okay, a 500 kilo kVA transformer has a primary winding resistance of 0.5 ohm and secondary winding resistance is 0.001 ohm. The iron loss is 2.5 kilowatt and the primary and secondary voltage are 5 kilovolt and 320 volt respectively. So if the PF of the load is 0.85, determine the efficiency of the transformer on full load and then on half load. So first of all, we have to identify the information given. Okay, so 400 kVA is your S value or apparent power value. And then 5 kilovolt is primary voltage, so VP, and then 320 is your VS. Okay, and then 0.5 ohm is your R1. Okay, this one is your R1. Okay, primary winding resistance, and then secondary winding resistance is R2. Okay, so primary is R1 and secondary winding resistance is R2. And then iron loss, this one also you can write it as P core. Okay, iron loss or core losses, so 2.5 kilowatt, and then your power factor is 0.85. Okay, first we calculate the efficiency on full load 4A. So let's see the step. So this one, all the information given in the question. So at full load, okay, I1 equal to S over V1. So this is actually from the formula S equal to 1 also can be right is primary, okay? So SP equal to V1 I1. So V primary, I primary. So this one can be right as primary. Okay, and then or secondary. Okay, so S equal to V primary, I primary. So to get I, so I primary or I1 also equal to S over V primary. So you will get ATM. Okay, therefore P copper at primary equal to I primary square R primary equal to AT square times 0.5. So this is your primary resistor winding 0.5. You will get 3200 watt. Okay, next step, you have to find I secondary. So S equal to, so this one you assume ideal transformer where V primary S primary equal to S secondary. Okay, so this one also use the same to I2. So to get I2 S over V2, so you will get 1250 ampere. And then copper loss at primary is equal to this one is secondary. So copper losses at secondary is equal to I secondary square plus R secondary. So just substitute the value here. And then R2 is 0.001. You will get copper losses at secondary is 1562.5. So this is at primary and secondary. So the total losses of copper, so you have to add P copper at primary plus P copper at secondary. So you will get the total copper loss. And then total losses. So total losses is core loss plus total copper loss. So that's why this one core losses already given 2.5 kilo. So 2500 watt plus total copper here. So 4762.5. Okay. Okay, so these are the formula for total losses happen in transformer. Total losses in transformer equal to core loss plus copper loss. Okay, and then output power is equal to S times PF. So S 400 kVA times your power factor 0.85, you will get 340 kilowatt. So this is output power. And then to get the input power, okay, input power equal to output power plus total loss. So you will get 347.26 kilowatt. Okay, and then to get the efficiency, you use this formula. Efficiency equal to 1 minus losses over input times 100%. So 1 minus, so your losses is 7.26 over your input power is 347.26 kilowatt. So this one you neglect the kilo, so you just use 7.26 over 347.26 times 100%. So the efficiency at full load is 97.91%. Okay, so this step is very important for you to understand. Okay, at full load. So once you already complete the efficiency at full load, so next you have to calculate the efficiency on half load. Okay, so for half load, so at half load, since I square R loss varies as the square of current, so to get, so at half load, the step is simpler compared to full load. So since I square R losses varies as the square of current, so to get the total copper, so you just, okay, so this is total copper loss. You already calculate at full load, so 7262.5. So 4762.5 times 0.5 is your, okay, 0.5 is your winding resistance at primary square. Okay, so you will get the total copper for half load is 1190.6. Okay, and then so you already skip this calculation because you can strictly get the total copper loss at half load using this formula. Okay, so total copper loss at half load is, so total copper total P copper, which you calculate at full load times R1 square. So you will get 1190.6. So to get the total loss, so total loss is equal to P core plus P copper. Okay, so you will get P core already given, which is 2500 watt. So plus total copper here 1190.6, you will get 3690.6. And then follow the next step, find the output power. Okay, so to get the output power, S times PF times 0.5. So 0.5 is your R1. Okay, you will get 170 kilowatt. And then the input power, same formula at full load. So input power equal to output power plus total loss. So your output power is 170 kilo. So this is your output power from this calculation, plus your total loss 3690.6 kilowatt, 3.69 kilowatt. So you will get 173.69 kilowatt. So, and then you have to get the efficiency from this formula. 1 minus loss over input times 100. So 1 minus, okay, loss 3.69 kilo over your input power. So 173.69 kilo, so we'll get 97.88%. Okay, so this one, please try the example 2 and then please submit to me in ULearn after your classes. So you have the step is same with example 1. So you have to find the frequency on full load and then frequency on half load. Okay, and then for open circuit and short circuit test, this one is actually the subtopic for lab 5. So what is open circuit and short circuit test? So these two tests enable the efficiency and the voltage regulation to be calculated without actually fully loading the transformer. So the objective of open circuit test is to determine the magnetizing impedances, and then for short circuit test to determine equivalent impedances. So results from both tests provide the parameter to the equivalent circuit as referred to primary. So this one is actually, you can compare from the calculation we have discussed to get the equivalent circuit as refers to primary, from calculation to a lab practical. Okay, so this is the connection to do the open circuit test, and then calculating magnetizing impedance using this formula, and then this is the short circuit test, then calculating equivalent impedance for short circuit. So that's all for part B, chapter 5. So hopefully you can try the exercise in chapter 5. So any question So please discuss in WhatsApp group. Thank you.